Who knows how awkward it is to hear this on the recording in progress too is even being recorded. So it's my wonderful pleasure to be able to introduce Anjali Fernandes and welcome here to Minnesota. Anjali has a long history, actually including a bit of time in a summer program here at the U, but then going all the way back to her early career, which she started in sedimentary geology. So Anjali started out at the University of Mumbai before she did her master's at IIT Mumbai. And then for reasons that I actually have never really asked you about, you crossed the world ocean to a strange and faraway land where people speak funny. They were, at least around 2010, it was very egalitarian. Men and women both wore skinny jeans and cowboy boots. And when she finished up at the University of Texas at Austin, Anjali had worked actually with David Morrig, another native Minnesotan who had done a postdoc here, and had studied in the field, had run physical experiments. And those two things, combining experiments and field with some idea about theory and how the sedimentary world works and operates physically, are things that she carried with her to her postdocs at Tulane University, where she continued her experimental work and started bringing things into more the modern, where she was starting to think about sea level rise and subsidence and coastal sustainability. She then took that show on the road up to the University of Connecticut, where she was a lecturer, working and started to bring in some other aspects in biogeochemistry. So thinking about kind of more what's happening in the full ecosystem, what's happening on the Earth's surface. From UConn, she then went to Madison University, where she is now as an assistant professor. And Anjali is very research active, very grant active, and being at a liberal arts college, that creates very creative ways to work with those grants, which she has become, better for worse, an expert at. But one of the big things is being able to involve large groups of undergraduates with diverse skill sets in her research. And I think we're going to see some of that today, as well as some of her collaborations. With that, Anjali, do you have a microphone?
So, I think I'm supposed to get the lights. Oh, okay. Well, at least it's not an embarrassing window. I closed everything before we projected it up there. So thank you for having me. This is a great pleasure to be here. The last time I was visiting this campus was 2013, I believe, and things have changed, including the nice fancy building. So again, thanks for hosting. Today I'm going to be talking a little bit about river dynamics in context of environmental change through deep time, integrating a few aspects of experimental work, as well as biogeochemical reconstructions with process sedimentology and physical sedimentology, which is what I do. Before I go any further, I want to acknowledge an illustrious list of co-authors, specifically Michael Wren, Virginia Smith, and Dennis Terry, who are co-PIs on a lot of the work that I'll be showing today, but also an extended list of graduate students and undergrads that have contributed in very creative ways to this project. Before I go any further, I also want to acknowledge funding sources, as well as a lot of infrastructural support that came from different universities and several additional undergrads that have been running samples in my lab for the last few years. Right, so getting into the goals of what we'll be talking about today, broadly defined against the backdrop of climatic change in Central North America, global climatic change and its impacts on landscape dynamics in Central North America. While I care about the details of what was happening on the landscape, I want to draw everyone's attention to the overarching goal of this work, which is primarily to bring together people who study ancient ecosystems and use proxies from these ecosystems to understand climate and ecosystem dynamics. Process sedimentologists like myself who study stratigraphy but work at a range of scales and care about how catchment scale processes influence what we see in a single outcrop. And environmental engineers, civil engineers who want to build models that are effective at projecting how climate change is actually going to impact human timescales. And so here is the key goal of the overarching project. So in terms of motivation, when we think about these different disparate fields against the broad backdrop of environmental change, we have a lot of different timescales in deep time that could be creating shocks to the system and producing landscape change. This is the estimated scale at which anthropogenic climate change would be working. And when we try to draw together different fields, whether you care about climate proxies or river landscape change from stratigraphy, many of these timescales can be either very short or potentially quite protracted, depending on the scale of bias that is included in the reconstructions from any kind of terrestrial proxy. When we think about river landscapes, you might have different kinds of sedimentary structures or whole fluvial stratigraphy columns that, again, are constructed at a range of timescales. If you care about bed forms, they could be existing or evolving anywhere from the scale of minutes to years, if you're thinking about fluvial bars and point bars. But once we start scaling up, the width of an entire channel belt is something similar to a millennial scale sedimentary package. And so when we start to think about current geomorphic models, the kinds of models that are used to project landscape change, they are very rarely built on the timescales that involve multiple generations. And when we look at all the disparate timescales that are available from deep time, really the only timescales that match are the timescales of channel adjustment from deep time stratigraphy and the potential creation of whole channel belts. And so integrating all of this information to push the boundary of our geomorphic modeling tools is going to be kind of a very fun way to approach this. Given that Earth's sedimentary record is literally the only pristine data set that is relatively undisturbed by humans and might be the template against which we can match any kind of our model outputs. So again, broad backdrop is going to be the Eocene, Oligocene climate transition in Central North America. Broadly, we saw several degrees of temperature change globally to do with the onset of Antarctic glaciation. And we see a lot of climate variability around this time. But when we try to reconstruct the impact on terrestrial landscapes, globally, we see significant differences and variability in what was actually recorded in terms of temperature. Some of this may be associated with different proxies that were used. Some of it might also just be regional differences. And so the questions that we ask now are, what was the impact of landscape dynamics on what was actually generated from these proxies? So a little bit of background here. We're dealing with the Eocene Oligocene climate transition about 34 million years ago. This is the marine isotope record, which suggests several degrees of cooling during this time. This is a terrestrial record created from fossil bone and tooth enamel. And again, in Central North America, the suggestion is there was several degrees of cooling. Looking at the stratigraphy now, quick note, a lot of this work is going to be in Nebraska. So the outcrop spread is relatively limited. Right here, we have the stratigraphy through this transition. The onset of the Oligocene is right at this boundary between these two packages. Don't worry about remembering all the names. They're not terribly important. Key things that I want you to observe, though, are for the late Eocene, we see a lot of white sandstones with very red paleosols. We see a lot of mud-rich, grayish fluvial sandstones and overbanked mudstones in a younger unit. And then once we get into the Oligocene, we start to see a lot of these tabular sandstones in the floodplains with, again, quite sand-rich channels associated with it. Just to give the game away a little bit, these tabular sandstones are interpreted as crevasse splays, so frequent overbank deposition. So again, some of the details might feel a little bit overwhelming here, but I want you to focus on the big picture. And so what we're going to be talking about is a very broad workflow where we're building biogeochemical proxies into stratigraphic information, reconstructions of sediment flux, to figure out what kind of modern systems would be good analogs for what we're working with in deep time, present that to the geomorphic modeling folks, and take it to the next step. Finally, the hope is that the outputs from a lot of these short or intermediate timescale models, I say short because I come from deep time, so this is not millions of years, it's millennial scale, but really it's long time scale for the engineers. But ultimately, what the hoped for goal is synthetic stratigraphy from the models, output back to my group, where we're now comparing millennial scale deposition. Okay, so just to get started, we're going to begin with a lot of the SED-strat information here. And rather than go through the whole interval, I'm going to use this as a proof of concept for the next step. So we're only going to be focusing on the youngest deposits right here. So when we look at this, when we see a bunch of channel stratigraphy where we see clearly defined bars, so these cliniforms that you see are river bars, they give us a proxy for channel depth. And so one thing that gives us is depth of the channel. When you have the width of the bar, it scales with the width of the channel. And so ultimately what that can help us reconstruct is some version of what the hydraulic geometry of these channels was. And so using that, this was work done by a very large group of undergrads who went into the field and measured a ton of bar deposits. For this specific outcrop, we have a large number of data points, but a relatively small number of robust measurements. And largely that's to do with preservation bias in the sedimentary record. Some of it is also about exposure bias. The orientation of the outcrop might not be just right for you to get a cross-channel measurement of width, for instance. When we look at the sedimentary record here, there's a lot of qualitative information that we can assemble. For instance, we see hoof prints with scattered blobs of mud, suggesting a channel bed that was recently wet but is currently drying out. We see mud cracks on the channel bed. By contrast, there's also a lot of high transport stage sedimentary structures. We see climbing dunes, we see a lot of climbing ripples. All of that tells us that we're seeing a lot of, in a very qualitative way, we're seeing a lot of variability in discharge. This tells us that base flow was probably hovering around 0 meter cube per second. When we look at the composition of high transport state sedimentary structures, in this case, climbing ripples, we can use climbing ripples to figure out what the grain sizes in suspension were. If you care about any of this, by all means, go to town on it, but you don't need to care about it. So take me at my word when I tell you that from there, we can get to some estimate ultimately of how fast the water was going, what the width of the channel and the depth of the channel was, allows us then to figure out what the peak discharge would have been for these events. When we look at bed load through the systems, any kind of sedimentary structures like dunes or plain stratification tells us that we're dealing with bed material load. And there's been a bunch of work, some of which has come out of SAFL and University of Minnesota, that shows us that we can relate the grain size of the bed material and the flow depth, so the channel depth, with the slope of the system. And from there, ultimately estimate what the sediment flux through these channels were. By the way, I want to acknowledge my undergrad who took the lead on some of these. Her name is Mia Rhodes. Ultimately, what this gets us to now is the first step in identifying a system that might be a worthy template for these rivers. And so once we have the bed load flux, we can compare it to a few modern systems for which we have these measurements and say, okay, that might be one candidate for which we can start to look at geomorphic models. Is there anything I can do about that bar at the top? Oh, okay, never mind. Right, so take it a step further. Vamsi Ganti and his student who have worked on this quite a bit. I mentioned Vamsi because he graduated from Minnesota, produced some really remarkable work where we were able to now use the thickness of dune cross sets to ultimately estimate what the bed topography was, so the scale of the average bed form on the river channel bed. Interesting.
Thank you.
It's been a while since I've used Zoom. I don't miss pandemic teaching. Right, and so once we sort of estimate the dune scale topography on the riverbed, again, we have a means of comparing. You'll notice that the North Loop is starting to show up a little bit more often now. One of the things that my favorite sedimentary structure is the climbing ripple. It's beautiful, but it also tells us so much about the river flow. And so here we have a bunch of climbing ripples and climbing dunes, and these rivers carried a lot of sediment in suspension, and there's an abundance of these sedimentary structures. And what that gives us ultimately is a way of estimating sedimentation rate. But finally, because we have a way of estimating sedimentation rate, and we use this by saying, okay, if this is the shape of your bed form, and you preserve that shape as it migrates both forward and upward in space, you can figure out how much sediment was deposited. But not only that, if you have a sense of how fast it moves forward, then what that means is you can also figure out how fast it was moving upward. And so you get that deposition rate. And so ultimately, we can go from deposition rate, use the thickness of the deposit beds to figure out roughly what the duration of the depositional event was. If your assumption is that this is suspended sediment during a flood, the ramping up stage is not what's preserved in this deposit, but the depositional stage at the end of the flood. So it's a fraction of the overall flood duration. So ultimately, again, I want to highlight that although we can put all of this information together, the actual information isn't what matters. It's really the workflow. The challenge here is always going to be preservation bias, the availability of enough outcrop, and outcrops with the right orientations to take the measurements that we need to do these kinds of specialized reconstructions. Moving on, we're going to talk a little bit about biogeochemical proxies. I'm going to give you just a taste of what the catchment reconstruction for this particular unit looked like, but then I'm going to step forward and talk a little bit about some of the biases that we've been working on to try and figure out how surface dynamics impacts what we're measuring. So returning to this section, when we talk about the entire reconstruction, I'll probably walk you through some of the measurements through the entire unit. But for the moment, we're just going to focus on this section. First, though, let me give you a little bit of a primer. When we deal with proxy reconstructions in this talk, I'll primarily be talking about biomarkers. And so biomarkers are leaf waxes that are used by plants to protect from evaporation, so environmental factors. They're an indicator of heat stress or water stress. And largely, they give us some sense of what that ecosystem looked like. When we use biomarkers, we're primarily using three things. We're using the stable isotopes of carbon, stable isotopes of hydrogen that are within these leaf waxes. And we're also using the heaviness of the wax or the length of the chain of wax that actually tells us a little bit about how much protection these plants needed. And so when we look at the stable isotopes, very broadly defined, if you want to think about how isotopes work, as you move inland and as you move up altitude, you get isotopes in the water that is rained up. These isotopes are taken up by plants. Plants die. Organic matter is deposited on the landscape or potentially mobilized downstream. This starts to be important when we start to think about the impact of transported organic matter on the signals that we're recovering. When we think about the context here, both the up topography signal as well as any kind of potential orogenic impacts from the cordilleras matter. And so we have both the North American monsoon coming in from the Gulf, as well as potential westerlies bringing moisture across the cordilleras. Right, so as I highlighted earlier, leaf waxes can give us a pretty decent sense of what exactly was happening on the landscape in terms of different kinds of plant species. The reason we use it in the geologic record is that it's actually quite well preserved over time. Provided that you don't have intense heat within your sedimentary basin, leaf waxes tend to be pretty well preserved. So just a little bit of, to sort of give you a sense of closure about the unit that we were looking at earlier. These are reconstructions done by Bailey McGuinness at University of Connecticut, who put together both average chain lengths, hydrogen isotopes, as well as carbon isotopes. And without belaboring the details here, I've put in red what this actually means. And so broadly, we're looking at a system where we think we have roughly 60 centimeters of precipitation a year and a catchment elevation of about half a kilometer. And so what we have now is this holistic view of what that catchment looked like, as well as what the river deposits look like that ultimately resulted. But no tool comes without bias. And so this is stuff that we've been working on recently and stuff that I've been pretty excited about. When we think about organic matter moving through a river system, you have organic matter that is transported from the catchment through the rivers, deposited in your river bars, and that might be accumulated in your channel deposits in the stratigraphy. You also have fairly stable floodplains, right? You have floodplains that are rarely visited by flow, where you're growing plants, the plants die, deposit material, build up your soil layers. You might also have relatively active floodplains, like the regions where you're building levees, where you have both transported organic matter coming through from floods, deposited on the floodplain, and then the signature of local plant growth superimposed on that. And so there's the possibility here of having a transported signal in our biomarkers, some sort of mixture of a local as well as upstream signal, and potentially something that is a little bit more local. And so the question here is, if your rivers are migrating about in time, how does the rate of migration or revulsion actively impact what we're reconstructing from the biomarker record? So as Andy mentioned, I trained as a sedimentologist and an experimentalist, and I always come back to experiments to understand big questions. And so here are two experiments in which water and sediment are moving through a delta basin. You've got two distributive systems. The only difference between them is that this system has twice the water flux than the other. And so on the right, you see that there's generally more water, but you'll notice that the channels tend to stay in place for a little bit longer. The floodplains, the white stuff, the dry sediment, tends to stay dry longer. And that's reflected in the two maps that you see on each corner, where the colors are floodplain age. So that's the age of the floodplain, which is definitely more in the right-hand side experiment than the left-hand side experiment. And what that tells us is that the movement of the channels is basically controlling how long each floodplain has to accumulate a local environmental signal. And so if you have parent material that's bringing organic matter from a catchment versus something that is growing in place, how long does it take to transition from a floodplain that primarily holds upstream information to a floodplain that now primarily holds in situ information? And so what we're seeing here then is that as we sort of step through time, each of these images, broadly, because you have more stable channels and more stable floodplains in a system with higher ratios of water to sediment flux, you tend to have older floodplains. In other words, you're priming the system to preserve more local environmental information, whereas the channels would hold on to catchment averaged information. If we sort of transition into looking at what the ages would look like, if we look at the oldest ages in your right-hand side experiment with more water flux, they tend to be nearly double of what the left-hand side experiment shows. In other words, channel dynamics fundamentally influence the kind of signal we can recover from our floodplains in terms of climate. In a more quantitative context, there's a probability of finding more in situ signal in a more stable floodplain or in a less dynamic river system, and more basin averaged or catchment averaged information in a more dynamic system. And ultimately, how do we know what's more dynamic or less dynamic? We look at the sedimentary record to figure it out. So this now brings me to a more holistic view of the entire section. What we've got here are the three major proxies that we've used. You've got hydrogen, the two major proxies, I didn't have room for the third. Hydrogen, carbon, and we're going up through the system. And so you noticed I pointed out extremely dynamic floodplains up there with a lot of crevasse play suggestive of a lot of flooding pretty frequently. We noticed that when we look at the isotope signatures in the floodplains relative to the channels, there's not a whole lot of difference all the way up there. However, in the well-developed paleosols, where you see this nice deep red, white channel sandstones, we see very distinctly different signals. The channels suggest that you have very high topography. The organic matter in the channel suggests that it was coming from very high topography in excess of about 2 kilometers, whereas the floodplain signal, the local signal, is quite different. And so what this tells us is, or what this tells me, and you're welcome to argue with me, is that channel dynamics fundamentally influence what we can recover from the sedimentary record. And I'll take it a step further and say, pulling out biomarkers or pulling out any kind of proxy from the sedimentary record without a broad context of what these channels were doing and a sedimentary context for our reconstructions could be potentially problematic. So looking at this, a very sort of initial or preliminary analysis is that we're dealing with pretty stable floodplains in the late Eocene, gradually transitioning to pretty active floodplains, and that has now changed the kinds of signals that we see in channels versus floodplains. On a positive note, what it does tell us, though, is that when you have a relatively stable channel system, you have information about your catchment and you have information about your local floodplain, your local environment, sorry. So once again, just a quick reminder, right there was a major environmental climate shift, but we see quite a difference in how channels and floodplains hold on to their different records earlier on. And that difference, that offset between channels and floodplains, is significantly larger than what the actual climatic shift should be reflecting in the sedimentary record. So this is problematic if we don't actually understand the sedimentary context for what we're sampling. Right, so just a quick recap. When we think about recovering any kind of proxy from a fluvial sedimentary record, we need to keep in mind that the channel dynamics and floodplain dynamics are quite key to what exactly we're pulling out. And ultimately, just to give you a sense of closure for the catchment and river stratigraphy we were just talking about, we do have estimates now for how much precipitation we were expecting to see in those catchments and roughly what the paleo elevation was. And so taking it to the next step, we use a simple search using those criteria, the reconstructions from sedimentary strata and reconstructions from biomarkers to assess what would be good rivers to use as templates to give the engineers for the forward geomorphic models. And so here we have the laundry list of everything that we've put together. I put in a reminder that we're looking at dynamic floodplains. And ultimately, where we're going is showing that there's a sound basis for the kinds of catchments and paired rivers that we're using for the geomorphic models that come with the next step. So quick acknowledgement of my undergraduate student, David Luffman, who did some of this scaling work. We still have a ways to go here because we did it as a proof of concept. We decided to focus on the high plains. The high plains, unfortunately, have seen quite a bit of uplift since the time that we were studying. We think that there's not a huge change in some of the hydroclimate conditions then versus now. But first cut, what we did was we used everything that came out of Mike's lab. So that's the reconstructions of hydroclimate and everything that I and my students put together to figure out what kinds of streams might be the best fit. And so here you see a range of catchment elevation for the high plains. You have annual precipitation as well as catchment elevation. This would be the reconstruction from biomarker proxies. The pink boxes and pink lines indicate the reconstructions from strata or proxies. And finally, we have discharge reconstructed from strata against modern drainage area for an estimate of what we might be looking at in the ancient. Broadly, the key takeaway here is that the North Loop keeps coming up as a viable potential template. but we had the best data from the NESCA. So the most number of gauges, it worked well with a lot of our scaling and reconstructions from deep time. And so ultimately we chose the NESCA as the template for these river systems. And so with the catchment information, with the modern river hydrographs, and whatever we knew about sediment transport through the system, which isn't very much, arguably, PhD student Mohammed, working with Virginia Smith at Villanova, has been putting in a ton of work to do what looks like 3 simple steps, but really isn't, to generate really long-term hydrographs that he feels are statistically robust. And this is not an easy task because the average record is about a few decades long, already influenced by human activity. And so how do you build out that record to run for a few hundreds to thousands of years and then start to even think about accelerated geomorphic modeling? The next step, so Mohammed has already finished this step. He's submitted a paper about it. To totally invite him to come give a talk here. The next step is the geomorphic modeling. And this is, as any modeler knows, extremely anxiety inducing because anything to do with sediment transport modeling is just so computationally expensive and time intensive. And so what Virginia and Mohammed are doing is doing a whole bunch of clever stuff that I can only hope to understand one day. But the key thing here is that they're using morphologic acceleration and physics-based AI to accelerate some of these steps. And so that's stuff that is currently getting written up. I'm not going to talk about much of this until I come back in a few years and tell you how we tested the stratigraphy. Ultimately, Mohammed's work has been primarily to go from hydroclimate. So what is the precipitation and approximate temperature, but primarily what is the precipitation in a given catchment with certain vegetation attributes, soil attributes? How do you go from precipitation on that landscape to a discharge record that can reflect any changes in weather that is ultimately induced by changes in climate? And so what he's done here is he's taken both observed and simulated long-term records. This is just a snapshot of a short-term record from the NESCA, but he's built it out over a couple of centuries and tested it statistically. I'm not going to go into the details. I could not possibly do it justice. Ultimately, this work, the hope is that once we get to the point where we can say, okay, here's your flood, it's depositing sediment on the floodplain. Here was the shear stress associated with that suspended sediment. Ultimately, here's the grid with grain size. And that's something that I can actually test in outcrops again. And so finally, we're going to hopefully not just look at the bed scale, but also the channel belt scale. So how wide was the channel belt? How thick was the sand body that was generated? How abundant are the crevasse plays within a given window in the outcrop, and so on. Right, so just to summarize, I think I've been speaking too quickly. When we think about sort of, I was right at the cusp of that sort of SEDSTRAT generation where almost every bit of research was funded by the oil industry to where we were beginning to think about environmental problems. And part of that switch was a lot of people saying the sedimentary record is the key record that we should use to test our models, right? And so that was always something that was in the back of my head. I was like, yeah, it totally makes sense, except that all of the models that we were building were for stratigraphy on million-year timescales, which is not a human timescale. It's not the timescale over which we care about how climate change is going to impact the landscape, right? And so it's inescapable that if we want to look at how those landscapes evolve, yeah, there's ways to test it against outcrop data, but we need that intermediate step, which is generating the models that we can test. And so ultimately, the fine scale, the sedimentary structures that tell us about sediment flux, the channel scale that tells us how wide, how deep the channels were, those are key pieces of information that we can hand to a civil engineer, for instance, who works with the model ultimately generates what the potential forecast could be, gives us some kind of long time scale, millennial scale sedimentation patterns that can then go back to the outcrop. So this is not operating on the scale of millions of years of climate change and landscape response. However, so as we start to pull it all together, you know, we were young, bright-eyed and bushy-tailed, and we encountered many problems along the way. And so now we are chastised and careful. But still, lots of interesting problems along the way to solve. The key here is that it takes a lot of time to develop the common vernacular to speak across boundaries that are engineering, geology, biogeochemistry, paleopodology. But the patience pays off, maybe not on the time scale that one goes up for tenure, but it pays off eventually. When we start to think about some of these interesting questions, I think the next steps for a lot of this work is to really understand the bias built into the proxy record, especially when we're using terrestrial proxies. Right, and so when we sort of put everything together, I think I've already said this, but both the fine scales, the minute, hours, days, weeks, years, decades, matters for the channel belt stratigraphy, because that's key information that might actually help us build, for instance, a flood distribution hydrograph of flood duration. What is the word I'm looking for? Flow duration curves. There we go. Something that is actually useful to engineers that are willing to work with geologists. But ultimately, working at the stratigraphic level, where we're producing sedimentary packages that were generated on that time scales, is going to be equally important. So the next steps, there's a lot of work for Mohammed before we can take it to the next step and actually figure out whether we can get those two pieces to talk to each other. But that's basically where we are. So thank you for listening. I'm sorry if I was talking too quickly.
Thank you. I'm just going to pass this back and forth to Anjali and actually pass it back to her once so she can manage the questions. And just so you know, here first we open the floor to students who are, for reasons still unknown to me, mostly sitting on the left side. This could be talking about like politics and generations, be talking about many other things. I don't know. We can find out. We can ask later. And the only announcement that I have is that, so I'm hosting whoever wants to come with Anjali tonight. If you didn't RSVP, as usual, I bought extra food, so feel free to come anyway.
Yeah, so what I didn't double down on is really when we think about the spatial integration of information, what you're doing is if you have a more dynamic system, most of the climatic information in your organic biomarkers present in floodplains and channels is transported information. And so what we have then is a really large spatial footprint for what that information gives us, as well as potentially a very large temporal footprint. So the granularity with which we can explore different climate events or resolve different climate events could be significantly different. On the other hand, if you have a more stable floodplain, what you're doing is, yeah, the channels are bringing information down from the catchment. And so you have elevation, you have some sense of what ecosystem dynamics would have been over a very large footprint within the catchment, but also locally, if you have enough buildup of organic matter, you have a very strong local signal. And so potentially you have two kinds of information that you can pass out there. Yeah, so I did a good job of not putting all the extra slides into this talk. And so I don't have it on hand, but while we are focusing on the climate transition in Central North America around this time, we were dealing with potential orographic effects from late stage uplift in the Cordilleras. I haven't seen any of that information in the strat section. So I've not been able to, for instance, reconstruct changes in channel gradient. So we don't think we're seeing that. It's unclear whether there are other ways it's being expressed. The other issue, which I love, is that we had a lot of volcanic activity around the time where you saw things to get a little bit, begin to get a little bit more gray. That's primarily coming from the Great Basin, but my volcanologist colleagues say there was a lot more that I hadn't accounted for, which as an experimentalist, I love that there's unconstrained changes and sediment flux raining out of the sky. But what's cool there is we think that it's basically a lot of weathering of volcanic glass that was transported both through channels as well as potentially on the floodplains that gives it that signature. So for instance, the bed material load, right, in that section, the sample bed material load had anywhere from 40 to 90% mud, which is not possible in bed material load, which tells us that that was transported volcanic glass that was moving as sand, but then has weathered in place since deposition. So there's other things going on in there, all of which Virginia and Mohammed intend to account for in their models, but we're hopeful, cautiously hopeful. Yes.
Where's the big application of long-term model? First of all, the basic climate projection where
well, we could think about what it would look like with, complete hard engineering, or potentially use a few more just nature-based approaches to managing our systems. For instance, if we think about making some of our streams a little bit more mobile, for instance, and we haven't really covered this here, but when we think about how we're actually even beginning to think about changes in precipitation and how it impacts the river channel could just be firmly in place. Ultimately, what that still gives us is a reasonable what is the word? With reasonable fidelity, reconstructions of what flood discharge could look like. So even if you put hard boundaries on your channel margins, like firmly engineered channels, it tells us what the water flux could be, right? If you have an entire catchment, you rain on it, you model what it might look like. Ultimately, if our engineering models, our geomorphic models, once scaled to like the millennial scale and tested against the sedimentary record, we can make those little tweaks to any system and say, okay, well, if the channel's not moving, then all the sediment is going right through or being stored in the channel. And this is what the flood looks like. And so I do understand the question. I think that it's often hard to go like from the deep time record to, well, now we're on a man-made landscape, essentially. How do we translate the basic processes, the physics and the mass balances that drive a lot of like what's moving over the Earth's surface? Those basic numbers are still just numbers, and we can still work with them. Hima? Okay, so you would okay, so it wasn't on these slides, but basically when we reconstruct a lot of these records, there's not a ton of granularity in terms of the finer timescales. So a lot of the transients timescale, like the of system adjustment, is something that we probably aren't capturing with the sedimentary record in deep time, because the final version of what we see for any one channel is going to be whatever its stable state was. If we're looking at an entire river system, in this case, we were dealing with the million-year time scale. So it's not a single river channel system that was evolving through time, unfortunately. There was a lot of catchment scale changes through the time interval. So I'm not looking at a single catchment. And so I don't think that I can do that here. Okay, I think I didn't understand the question, sorry. Okay, so I see. When you like, what would it take to go back? Well, I don't know is the short answer, but I can speculate. If you're looking at changes in water flux, then you're looking at like a massive changes in the hydroclimate. So if we think, no, I'm not going to speculate. Sefo. I will add, though, that when we look at those experiments, to translate that to a natural landscape, we're going to be looking at the key timescales on that landscape too. So, for instance, if I say, there's a 50% probability of like the organic carbon on this landscape is this age, but or rather the floodplains on this landscape is this age, and it takes twice that amount of time to build up enough organic material on that floodplain to generate sufficient signal to be preserved in deep time, then what that tells us is that it's only going to be a basin average signal. I don't know whether I answered your question, but okay.
Yeah, so again, if you're going to not a sediment transport, but I have like a sediment transport question that's sort of in the same vein of the river system question. So when you're looking at, like, how do you go back and look at all this paleo sort of transport data? How do you kind of fit that in when you're looking at forward models, considering that there's so many landform changes that are not necessarily directly related to just like river and stream system, but also considering agricultural activity that's stabilizing slopes and then resulting in more or less sediment input to a system beyond just.
So again, that would be the fundamental inputs that would go into any of these geomorphic models once, assuming that we ever get to the stage where we can start building it out for climate change resilience, right? Again, it's just down to sediment flux, it's down to, changing water fluxes, but we would, then we start to look at geomorphic change on the landscape. So land use, any kind of, relative numbers in terms of sediment shedding from hill slopes and so on. But again, it comes down to having those initial constraints in place. And if we have them or have some sense of what they're likely to be, I say this flippantly, and I'm not trying to be flippant, that is still a sediment flux number that can then go into a model that says, okay, this is the area that is generating this much sediment, this much water to a channel with these dimensions, and let's run with it and see what we get. I don't know, does that answer? Yeah. Oh, yeah, sure. I can read it out for the room too. Are they related to the units exposed at the fossil beds? Yes. Climate ripple channels. Yes, there are. So the question here is, are the units that we're looking at related to the agate fossil beds in, I'm not sure which national park this is, but they are related and it's within this unit. So those are very popular agate hunter beds. Would it be optimal to study exposures occurring at different positions with catchments? Could that increase confidence in your models? So yeah, more data is always helpful when it's available. If you don't have enough exposure, then you might have to be a little bit creative about what you're going to be using. But yeah, more data, always better. If you have the money for it. So there's a lot of fossil beds out there. I'm not a paleontologist. I know that a lot of the work that I did to build some of this framework came from a lot of the work that was put together from the fossil literature. And so I'm aware of that. My limited understanding of why anyone would care about this if they care about paleontology is about ecosystem stability. And so if you have frequent floodplain inundation, and I think is the word deathbeds, like when you have like whole communities just dying in place. I think there are several deathbeds related to some of these units, both near where I'm working as well as somewhere out in the Badlands in South Dakota. But that's kind of the limit. I mean, also if you care about floodplain dynamics, it matters for plant growth and animal activity, how wet it was and what the water table was, because you have burrowing animals. Prairie dogs, I think, are burrowing animals. Like the paleo version of prairie dogs have their burrows, and those burrows usually bottom out right above the water table. And so how deep they can go and therefore how safe they are from predators probably is related to how wet your floodplains are, which ultimately comes back to hydroclimate. I'm not sure if I'm answering or rambling at this point.
Starting to get towards wrapping up. If there's one last question, someone raise their hand quickly. Otherwise, let's thank Anjali one more time.
Thank you.
Is there cheese on the fourth floor? There. Yep. Yeah. Okay. Cool. Fourth floor.
Do I just pick it off? I'm returning everything. Okay. Screen sharing stopped.
Good.